In this example, we'll use the definition of the derivative to find the derivative with respect to x of f of x is equal to x to the third minus x. Remember, we'll start with the average rate of change over the interval from x to x plus h. I've put down these values here since we've done them several times already. Okay, so at the one end of the interval, the x value is x. The y value is given by the function, so it would be x to the third minus x. At the other end of the interval, the x value is x plus h, so the y value is the function where each instance of x has been replaced by x plus h, f of x plus h. So instead of x to the third, we have x plus h to the third, minus instead of x, we have the quantity x plus h. Be careful, many students forget these grouping symbols here, and in essence will make a mistake on the sign of h. All right, now we know that the change in x is x plus h minus x, which is h. We've seen that before. The change in y is the difference in the function values. In this case, it's the quantity x plus h to the third power minus the quantity x plus h. This is f of x plus h. All right, and we'll subtract the quantity x to the third minus x. Again, we have to subtract all of f of x, so we have to subtract all of this. So I put it in grouping symbols so we know that we're subtracting the entire thing. Again, if you forget those grouping symbols, you will change the sign on this last term. Right. Then the average rate of change in y with respect to x, or in f we could say with respect to x, is going to be the change in y divided by the change in x. All right, to get f prime, okay, we'll take the limit as h approaches 0 of this expression. Remember, the idea is that basically we have smaller and smaller changes in x. So that as h goes to 0, the change in x from the left end of the interval to the right end of the interval gets smaller and smaller until when h approaches 0, there's no change whatsoever. Right. To take this limit, we'll have to expand and simplify the numerator. And so expanding this, well, first of all, I have to expand x plus h to the third power. I'll use the coefficients of binomial expansion, which come from Pascal's triangle, and we'd have x to the third plus 3x squared h plus 3xh squared plus 1h to the third. And then I'll have to subtract this x plus h. Getting rid of grouping symbols, remember we'll have to distribute this negative sign through both terms, so minus x minus h. Again, get rid of grouping symbols, distribute the minus sign. And so we'll have minus x to the third plus x. And this will all be divided by h. Well, notice a couple of things. We have an x to the third, and here we're subtracting x to the third, so they subtract out. We have a negative x, and we have a positive x, so they subtract out. And all the terms that remain in the numerator have a factor of h. So I can take out the factor of h, and I'll be left with 3x squared. In the next term, I'll be left with 3xh. In the next term, I'll be left with h squared. And in this term, I'll be left with a negative 1. This is all divided by h. And so the h's cancel. And so we're left now with the limit as h approaches 0 of 3x squared plus 3xh plus h squared minus 1. And this is a continuous function, so the limit, we would just be able to evaluate this where the h is 0. This would become 3x squared plus 3x times 0 plus 0 squared minus 1, or simply 3x squared minus 1. So in this case, if f of x is equal to x to the third minus x, then the derivative f prime of x is equal to 3x squared minus 1. Let's look at a graphic of this. Right, if we do so, right, notice I have two graphs here. The top one is f of x, x to the third minus x. The bottom one is the derivative of f prime, which is 3x squared minus 1. Notice here at x is equal to negative 2, x is equal to negative 2, well, I guess it's not quite negative 2, but at this value of x, the same value of x, all right, this run is 1, so this rise gives us the slope of this tangent line. This rise is exactly the same as the rise up to the graph of f prime, because f prime tells us the rise of, for a run of 1 on the tangent line, the instantaneous rate of change. As we go across, so notice, by the way, this tangent line has a positive slope. The derivative will have a positive value. Its graph will lie above the x-axis. As we go over here, right in about here, right, the derivative, the slope, of the tangent line is 0, and notice at that point the derivative crosses the x-axis. If we go a little farther, the slope of the tangent is negative, and the derivative is negative. The graph of the derivative for those values of x where the slope is negative lie below the x-axis. A little farther, and the graph of the slope of the tangent line is 0. The tangent line is horizontal. The derivative is 0. The derivative is 0. And finally, as we go further to the right, the slope of the tangent is positive. The derivative value is positive. The graph lies above the x-axis. So if you're given a function and we're wondering what the derivative looks like, it might be easy to find the places where the tangent line would be. The tangent line would have slope 0, and those would be the places where the derivative would cross the x-axis. Where the slope is positive, the derivative would be above the x-axis. Where the slope is negative, the derivative would be below the x-axis.